When we went from kinematics in the linear discussion or translational discussion earlier this semester into dynamics, we introduced the concept of inertia. We talked about Newton's laws, and Newton's first law stated that an object to be accelerated needed a force or a net force applied to it. Right? Objects in motion tend to stay in motion unless acted on by an outside force or an unbalanced force. We then introduced the relationship on how the force and the acceleration were linked. It was through the inertial mass of the object. F is proportional to A, but F equals mass times acceleration, where mass is a measurement of how difficult it is to change the motion of an object. Massive objects are hard to get going, and they're hard to stop once they're going, right? Think of a freight train. A lot of force needed to get that to accelerate, and a lot of force needed to stop a freight train from accelerating, to decelerate a freight train. So, objects in linear motion stay in motion unless acted on by an outside force, Newton's first law. But that also means rotating objects will continue to rotate unless acted on by an outside torque. Remember that torque is the rotational analog of force. So if you want to change an object's rotation, if you want to start an object rotating if it's at rest, or to stop an object rotating, you need to apply a torque to that object. So what is the rotational analog of mass, right? So forces cause linear accelerations, torques cause angular accelerations. But there's a relationship there. How much torque creates how much of an angular acceleration. They're proportional to one another. So you can say that the torque is proportional to the angular acceleration. But how are those related? So let's derive that. Newton's second law, right? F equals ma. We also know that the acceleration, the linear acceleration, was equal to the radius times of the object away from the rotation axis times the angular acceleration of that object. And that the torque, if the force is applied perpendicularly to the rotating object, the torque is equal to force times the distance that force is applied from the rotation axis. Well, I'm going to replace F equals ma, plug that F in here, and I get torque. Instead of F, I get force is equal to mass times acceleration. That R is still here. Now I have an equation here for acceleration. I'm going to plug that acceleration in there. So this mass is there. This acceleration becomes R times alpha, R times alpha. That R is still there. So you can see I have R in the equation twice, so I combine those. So the torque is equal to M times R squared times alpha. So here I said torque is proportional to alpha. What is the constant of that proportionality? It's this term mr squared. So here we have net force is mass times acceleration compared to the net torque is mr squared over alpha. Here's the rotational, here's a linear version of force. Here's the rotational analog of force, the torque. Here's the acceleration. There's the rotational analog of the acceleration. Here's the mass. This must then be, this mr squared, must then be the rotational analog of mass. How difficult is it to start something rotating? How difficult is to stop it when it is rotating? Depends not on just the mass, but how that mass is distributed. How far away is that mass from the rotation axis? So we call this term, mr squared, the rotational inertia, or another way of saying it, it's the moment of inertia. It depends on how the mass is distributed. So if I have something you probably all used at some point, in your life, baseball bat. This baseball bat is not symmetric, right? It has more mass on this end and less mass over here. But it has some mass. The total mass of the baseball bat is some mass m. So if I try to accelerate this bat forward and backwards, right, or side to side, F equals ma just depends on the mass of the bat. But if I try to rotate this bat, and that's how you play the game of baseball, right? You swing the bat. I'm going to have this rotation axis. You won't see the whole bat in the frame. But I'm going to spin it like this. So imagine my wrist into the camera is the rotation axis, and I'm going to spin the bat like this. That's actually hard to do, get it moving and stop it. Because more mass over here is far from my rotation axis. This is R. R is quite big. If I change it around, if I grab the mass part of the bat, now most of the mass is near the rotation axis, this is actually very easy to do. It's very easy to create an angular acceleration of the bat about my rotation axis when the mass is close to the rotation axis than when it's far away. I'm going to use two hands because my wrist is getting a bit sore. So you can try this at home. Grab a bat or grab something that has more mass on one end than another, a broom, for instance. Although a broom might not be a great thing because it doesn't have that much extra mass on one side. A baseball bat works really well. But yeah, just grab the fat end, easy to swing around. Grab the thin end, much harder to swing around. So it depends on how the mass is distributed with respect to the rotation axis. If I grab it in the middle, now the mass is close to the rotation axis, this is actually pretty easy to do as well. So we'll look further at this moment of inertia, and now because we've defined moment of inertia, that's the rotational equivalent to mass, we can then look at the dynamics equations for rotational motion. So the moment of inertia is represented by the letter capital I. So capital I is the rotational equivalent of mass, right? Mass is a measurement of the inertia, how difficult it is to get something moving or stop it when it is moving. Moment of inertia or rotational inertia, I, is the difficulty, right, of getting something spinning if it's not spinning or stopping it if it is. So the Newton's second law, if you will, version of torque is the net torque is equal to the moment of inertia times the angular acceleration. So if you know what the moment of inertia is of an object, and you know what torque you place on the object, what net torque you place on the object, you can determine that object's angular acceleration. And I depends on the distribution of mass with respect to the rotation axis. It's not just dependent upon mass, but where that mass is located. The further away a mass is from the rotation axis, the larger I is. And a simple example, imagine a merry-go-round. You're looking down from above. You have a bunch of kids on the merry-go-round, and you're trying to get the merry-go-round spinning. You're out on the edge, applying a torque, applying a force perpendicular to the rotation axis, trying to get this merry-go-round moving. Well, say you have a bunch of children on the merry-go-round. So the merry-go-round itself has some mass, and it has, so that mass is distributed from the rotation axis. So it itself has some rotational inertia. But each child on that merry-go-round also contributes to the mass and the rotational inertia of that merry-go-round. So it's much easier to get a merry-go-round spinning if all the children are in the center, and much more difficult to get that merry-go-round spinning if all the children are sitting at the edge, the outer lip of the merry-go-round. So different shapes have different moments of inertia because different shapes have different distributions of where the matter is, where the mass is in that shape compared to the rotation axis. So, for example, if you have a hula hoop or some kind of if you have a thin-walled cylinder, hollow cylinder, where all of the mass is located distance r away from the center of the rotation axis, assuming the rotation axis is in the center, you end up with a maximum amount of rotational inertia. All of the mass is located at some radius r. So the moment of inertia of a hoop about the central axis is just mr squared, where m is the mass of the hoop and r is the radius of the hoop. If you have a disk of material instead of a hoop or a ring, if you have a disk of material, then that disk has some mass close to the center of rotation and some mass further away. So the moment of inertia falls. For a disk or a cylinder about the central axis, the moment of inertia is just 1/2 mr squared. Again, where m is the mass of the cylinder or the disk, r squared is the radius of the cylinder or disk. It's easier to spin a cylinder than it is to spin a hoop. Finally, let's look at spheres. Imagine a solid sphere versus a hollow sphere. A solid sphere has some mass near the center of rotation, depending on, it's a sphere, so it's symmetric. It doesn't matter. As long as the rotation axis is going through the center, it'll look the same any way you spin it. So as long as the rotation axis is going through the center of a solid sphere, the moment of inertia is 2/5 mr squared. A hollow sphere has more mass away from the center of rotation, therefore it should have a higher moment of inertia, and it does. 2/3 mr squared for a hollow sphere. And hopefully you can see 2/5 is a bit less than half, 2/3 is a bit more than half, so I, for a hollow sphere, is larger than that for a solid sphere. I cannot be greater than that for a hoop. That's the maximum value you can possibly have. And if all of the mass is a point source right in the middle of rotation, there is no moment of inertia at all. So for point-like particles, what we dealt with before, we didn't worry about rotational motion because they can't have rotational motion. They're point-like. But now we're going to look at physically larger objects, spheres and cylinders, and talk about their motion. And they do have moments of inertia. Now the handout that I've given you, the unit conversion handout, also on the back side has moments of inertia. So you'll be able to look up those common moments of inertia. I'm not going to have you memorize them. In a more advanced physics class, you can actually calculate what the moments of inertia are of complex objects, like that baseball bat I had earlier. You could actually calculate what the moment of inertia is about some rotational axis. But that's more advanced. It requires calculus. So we'll stick with these very simple shapes, and I will give you the moments of inertia for them, or I will ask you to solve for what they are, given maybe alpha and the net torque, solve for I. So you can solve algebraically for I, or you can use your sheet or your textbook to figure out what the moments of inertia are for simple objects.